Hello everyone. Today we want to talk about 10.4, the divergence and integral tests, the second part. In this lecture, we will talk about the integral test. Let's take a look at the idea below. Suppose f of x is a continuous positive decreasing function for x greater than or equal to 1. Okay, so right here, continuous means that there's no hole, there's no vertical asymptotes, there's no gap. Okay, just like this graph. Okay, every dot is connected. Okay, and it's positive. That means the graph of y equals f of x will be above the x-axis. And finally, f is decreasing. That means the y values will become smaller and smaller and smaller and smaller, okay, as x increases. And right here, we let a sub k be f of k. And right here, k is a positive integer. So that means when you plug in positive integers, for example, you plug in 2, then f of 2 will correspond to a sub 2. F of 3 will correspond to a sub 3. So let's take a look at the pictures below. First, let's take a look at the picture in the middle. So right here, you can see that the pink region is enclosed by y equals f of x and the x-axis from 1 to 4. So that means the area of this pink region is given by the integral of f from 1 to 4. Now let's take a look at the picture on the left. You have 3 rectangles, okay, 3 yellow rectangles. Okay, and we know that the area of this yellow region will be less than the area of the pink region, right? Because right here we didn't count this white part, we didn't count this white part, we didn't count this white part, okay? So the area of the yellow region will be less than the area of the pink region. And to evaluate the area of the yellow region, we can evaluate the area of this and this and this rectangle and add them together. So notice that the area of a rectangle is width times height. Width times height. And right here you can see that the width is 1, the width is 1, the width is 1. And the height of this rectangle, the first rectangle right here, is this y value. And notice that here we have x equals 2, so that means the corresponding y value will be f of 2. And f of 2 corresponds to a sub 2. So that means the height right here is a sub 2. So a sub 2 times 1, that will give you a sub 2. So this area, okay, the area of this yellow rectangle, the first yellow rectangle, is a sub 2. Similarly, the y value right here is when you plug in x equals 3. So that will be f of 3, which is a sub 3. So height times width, you will have a sub 3. Okay, so we notice that a sub 2 plus a sub 3 plus a sub 4 will be less than the integral of f from 1 to 4. Now let's take a look at the picture on the right. And this time, the area of this green region will be greater than the area of this pink region because we overcount this green part, this green part, and this green part. Okay, so the area of the green region will be greater than the area of the pink region. Okay, and to evaluate the area of the green region, we want to use the same idea. We calculate the area of each rectangle and add them together. And the area of the first green rectangle will be width times height. And right here you can see that the height corresponding to the y value when x equals 1. And the y value when x equals 1 is f of 1, which is a sub 1. So you have a sub 1 times 1, that will give you the area of the first green rectangle. Similarly, the area of the second green rectangle will be a sub 2. So you get the integral of f from 1 to 4 will be less than a sub 1 plus a sub 2 plus a sub 3. Now let's say we have 1 more point 5 right here, and we will create one more rectangle, and we will create one more rectangle right here. So you can see that if I integrate f from 1 to 5, then it will be greater than a sub 2 plus a sub 4, a sub 3 plus a sub 4, and plus a sub 5. But this integral will be less than a sub 1 plus a sub 2 plus a sub 3 plus a sub 4. So by using this idea, we can get this inequality below. The integral of f from 1 to n is greater than summation of a k's, k star from 2 to n. And it will be less than summation of a k's, k star from 1 to n minus 1. So you can see that right here, if I choose n to be 4, then I will add a k's, k star from 2 to 4, right? A2, A3, A4. And right here, I will add a k's, k star from 1 to 3, A1, A2, A3. Okay, so you don't have to memorize this inequality. Okay, we just need this inequality to talk about the integral test. Okay, and if you want to create this inequality on your own, notice that it comes from these three pictures. Okay, these three pictures. Okay, so next, what we want to do is to take the limit as n goes to infinity. Okay, we want to take the limit as n goes to infinity. So right here, if you take the limit as n goes to infinity, this becomes an improper integral. And this becomes an infinite series. This also becomes an infinite series. Okay, so we get the integral test as below. Suppose f is a continuous positive decreasing function for x greater than or equal to 1. Now we need these three conditions because we want to create a picture like this. Okay. Now if you violate any one of the conditions, then we might not have this very good property. Okay. So that means in order to apply the integral test, we need to make sure that our function is continuous, positive, and decreasing. And of course, right here we assume that a sub k is the same as f of k for positive integers k. Then the improper integral f of x dx from 1 to infinity. Remember here I take the limit as n goes to infinity. So that's how I get this improper integral. And summation of a k's, k start from 1 to infinity. Again, I take the limit as n goes to infinity. I take the limit as n goes to infinity. Okay, so you can see that this integral is bounded by these two sums. So when I take the limit as n goes to infinity, they both, okay, well, right here you have 3, right? But when n goes to infinity, okay, basically we consider this infinite series. They both converge or they both diverge. Okay, so think of this. If this is convergent, then this will be convergent. If this is convergent, then this will be convergent. Okay, similarly, if this is divergent, then this will be divergent. If this is divergent, then this will be divergent. Okay, so the improper integral and the infinite series either both converge or both diverge. Okay, now before we practice some examples, here we have a remark. It is not necessary to start the series or the integral at k equals 1. Okay, you don't have to start from 1. Okay, for example, when we test the series 1 over k minus 3, the whole thing square, and when k start from 4 to infinity, we use the integral from 4 to infinity. Okay, we don't always need k start from 1. And here, the next one is very, very important. We should not infer from an integral test that the sum of the series is equal to the value of the integral. In general, the value of the sum and the value of the integral will be different. Okay, now the only thing we know is that they both converge or they both diverge. Okay, but we cannot say their values will be the same. Okay, we cannot say the values will be the same. Okay. Now let's take a look at page 2. In example 1, we have this series, summation of k over k to the 4th plus 1, k start from 1 to infinity. So in this example, we have two parts. Part A, we want to show that the integral test may be applied to this series. Okay, so notice that in order to use the integral test, you need to create a function. Okay, you need to create a function f, because we want to say that the series and the integral both converge or both diverge. We need to create a function. And then we have to make sure that the function is continuous, positive, and decreasing. Okay, continuous, positive, and decreasing. Okay, so let's start this example. Okay, so part A. So first, we want to create a function. And since we want the y value to be the same as the terms, okay, we want to create our function where when you plug in k, I should get this k over k to the 4th plus 1. So that's why right here f of x should be x over x to the 4th plus 1. Okay, and right here k start from 1, so we say that we want x to be greater than or equal to 1. Okay, so first set up a function. And then you will need to check 3 conditions. Whether this function is continuous, whether this function is positive, and whether this function is decreasing. Now, for continuous and positive, usually you just need to write it down. Okay, so f of x is positive for x greater than or equal to 1. It's obvious because right here, when you notice that the denominator is always a positive number, right? And if your x is greater than or equal to 1, your numerator will always be positive. And you divide a positive number by a positive number, the whole thing will always be positive. Okay, so usually we just need to write it down. Okay, and similarly for continuity. So f of x is continuous for x greater than or equal to 1. So basically we will do a really quick check. Do we have a vertical asymptote? No. Do we have a hole or a gap? No. Okay, so we just say f of x is continuous for x greater than or equal to 1. Okay, or you can say this is a polynomial, this is a polynomial. A polynomial over a polynomial is a rational function, okay, and a rational function is continuous on its domain, right? And the domain right here is x greater than or equal to 1. We cannot have any vertical asymptotes, so we are good. It's continuous for x greater than or equal to 1. Okay, now the third condition to say f of x is decreasing will be a little bit tricky. Okay, so right here, let's make a quick review. In Calc 1, we learned the relationship between the graphs and the derivatives. We say that if the derivative of f is less than 0 on the interval from a to b, then the graph of f will be decreasing on the interval from a to b. Okay, so right here, if we want to say f of x is decreasing, basically we want to show that the derivative is less than 0. Okay, so here we will need to find the derivative. So let's take the derivative. And notice that right here, f of x is x over x to the 4th plus 1. This is a fraction. Okay, it's a quotient. So how do we usually take the derivative of a quotient? The quotient rule. Okay, the quotient rule. Now, just in case you forget, recall that if you have f over g, you want to take the derivative. That should be f prime g minus f g prime all over g squared. Okay, this is the quotient rule. Quotient rule. Okay, this is the quotient rule. So right here, we wanted to take the derivative of x, which is 1, and we will keep the denominator. Okay, and minus keep the numerator, take the derivative of the denominator over, okay, all over denominator square. Okay, so let's simplify this really quick. Right here we have 1 times x to the fourth, but minus 4 times x to the fourth. So I have minus 3x to the fourth. And I still have a plus 1. And all over x to the fourth plus 1, 20 squared. Okay, so notice that x to the fourth plus 1 is always positive, and you square it. Okay, so that means your denominator is always positive. And your denominator is always positive. Now, when x is greater than or equal to 1, x to the fourth is always greater than or equal to 1. So that means negative 3 times x to the fourth will always be less than or equal to negative 3. And when you add a 1, this numerator is negative. Okay, and you divide a negative number by a positive number. So that means your derivative is always negative when x is greater than or equal to 1. Does that make sense? It's okay? So let me say it again. Because right here x is greater than or equal to 1, right? So you can just pick some number that is greater than or equal to 1, like 1.5. Okay, and 1.5 to the fourth will be greater than 1, right? And then if you multiply by negative 3, this guy will be less than negative 3. And that a number that's less than negative 3, if you add 1 on it, it will be less than 0. Okay, so right here, f prime of x will be less than 0 for x greater than or equal to 1. Okay, so notice that we are checking at the sign for f prime, but the conclusion is about f. Okay, so that means f of x is decreasing for x greater than or equal to 1. Okay, so right here, if you want to say more, you can say numerator is less than 0, denominator is greater than 0. Okay, if you want to explain. Okay, so remember, some common mistake that students made in the past is to say that f prime is decreasing. No, f prime is negative. F is decreasing. Okay, you cannot say f prime is decreasing or f is less than 0. No. Okay, so don't mess these two objects up. Okay, so now you can see that f of x is positive, f of x is continuous, and f of x is decreasing. That means our function satisfies the conditions for the integral test. Okay, our functions satisfy the integral test, the conditions of the integral test. So thus, the integral test applies. Okay, the integral test applies. So that means we may use the integral test. Now you can see that our problem has the second part. Now we want to use the integral test to determine if the series converges or diverges. Now you may say, wait, what? We didn't use the integral test at all? No. Okay, so notice that part A, we just check the conditions. Okay, we just check the conditions. In part B, we will apply the integral test. Okay, so you can see that this is a very long problem. Therefore, in general, usually when you have a series, you don't want to use the integral test directly, okay, unless the problem asks you to use the integral test, okay, because we will learn a lot of different tests later, okay, 10.5, 10.6, 10.7, okay, we will learn a lot of more tests, okay, and you can use those tests if you can. Okay, and the integral test is usually the last test you want to consider. This is because it's very long. Okay, you need to check the conditions and then you need to apply the integral test. Does that make sense? Okay, now the integral test says that the infinite series, the infinite series and the improper integrals, they both converge or they both diverge. Okay, so that means if you want to determine the convergence of this infinite series, we can determine the convergence of the improper integral instead, and then we get the same conclusion. Okay, so right here, we will need to evaluate. Okay, we will need to evaluate the integral of f, and my f is, I believe it is x over x to the fourth plus 1 dx from 1 to infinity. Okay, we want to evaluate this. Okay, so let's do it together. Now notice that this is an improper integral. And what is our first step when we want to evaluate an improper integral? We need to set out the limit, right? We need to set out the limit. So right here, we will need to find the limit of the integral of x over x to the fourth plus 1 from 1 to, because we have a problem right here, right? This is an improper integral of the first type. Remember the first type when you see infinity or negative infinity in your bounds. Okay, so right, that's why we need to integrate from 1 to t instead. And we will let t go to infinity. Okay, now this is an ordinary integral. So how do we evaluate this integral? We can use u substitution, right? So right here we will let u be x squared. Now you might be wondering, why do we want u to be x squared? This is because if u equals x to the fourth, then your du will be 4x cubed dx. Okay, but you don't have anything about x cubed. Okay, so notice that right here the numerator suggests that your derivative is x dx. Okay, x dx times the constant. Okay, we can always take that constant out. Don't worry about the constant. So the derivative is x dx. So that means your u should be quadratic. Okay, your u should be quadratic. Okay, then your du will be 2x dx. So that means your x dx is 1/2 du. Okay, so your x dx is 1/2 du. Okay. Now notice that this is a definite integral. A definite integral means you have upper bound and lower bound. So that means you also need to change the bounds. Okay, so when x equals t, right? This is the x value because you integrate with respect to x. So when x equals t, your u is x squared. That means your u is t squared. And when x equals 1, this is your x value. Your u is x squared, so 1 squared. It's okay? Good? Okay, so I will need some more space. So let me insert a blank page. So thus this integral becomes, okay, so this integral becomes, we still have the limit, okay, because right here all our setup, okay, this red setup is for the u substitution on this integral. We didn't touch the limit, okay, and now your new integral should be, here we have x dx, so that will be your 1/2 du. Okay, and x to the fourth, notice that u is x squared. So x to the fourth is u squared. U squared and plus 1. And plus 1. We have a plus 1. Okay, And then your new upper bound will be t squared, and your new lower bound is still 1. It's okay? Don't forget the upper bound and lower bound. Okay, so if you take a look at the previous exams, you can see that if you mess up with the new upper bound and new lower bound, you will get a wrong answer. Okay? Yeah, in some cases, of course, in some cases, if you are lucky, your answer will be the same. Okay, but in some cases, if you have the wrong upper bound and lower bound, your whole answer will be different. Okay, so let's finish this. Of course, you can take that 1/2 out because that 1/2 is, oh, what's going on? That 1/2 is a constant multiple. Okay, so you can take that 1/2 out of the integral, and you can also take that 1/2 out of the limit. Okay, because 1/2 has nothing to do with u, right? So when you integrate with respect to u, it's a constant multiple, and this 1/2 has nothing to do with t. So that 1/2 is also a constant multiple right here. Okay, so you can take that 1/2 out of the limit and the integral. Okay, and what is the integral of 1 over u squared plus 1? Now, if you remember it from calculus 1, you know that it is arctangent. Okay, arctangent of u. Okay, arctangent of u. Now, from 1 to t squared. Now, if you don't remember this, that's fine, because for u squared plus 1, this is trig substitution, right? It is of the form of x squared plus a squared, right? So in this case, you let u be tangent, okay? And then you can go from there, okay? Of course, right here, you can see that it's easier to remember from Calc 1 that this integral is arctangent, okay? But if you forget, don't worry, you can always use trig sub to get the same answer, okay? Then we will need to plug in upper bound. So we have arctangent of t squared minus plug in lower bound, arctangent of 1. Okay. Now notice that arctangent of 1 from pre-calc, we know that's pi over 4. Okay, we know that's pi over 4. Okay. So the question is, what is the limit of arctangent of t squared as t goes to infinity? Okay, so recall that the graph of arctangent looks like this. It seems like we talked about this before, right? I think so, in somewhere, right? This is y equals arctangent of x. Okay, and you can see that there are two horizontal asymptotes. This is x equals pi over 2. This is x equals negative pi over 2. So that means when x goes to infinity, your y will approach pi over 2. But when x goes to negative infinity, your y will approach negative pi over 2. So that means right here, arctangent of t squared, when t goes to infinity, you will approach pi over 2. Okay, so you will approach pi over 2. So you have pi over 2 minus pi over 4. Okay, so pi over 2 minus pi over 4 is pi over 4. Pi over 4 over 2, you have pi over a. Okay, you have pi over a. Now let's write down the conclusion carefully. So right here, pi over 8 is the value of the improper integral. Okay, so first we will need to say that the improper integral (1 to infinity x over x to the 4th plus 1 dx). This improper integral, now the limit equals pi over 8, and pi over 8 is a specific number. that means the limit exists. So the improper integral converges. Okay, converges. Of course, right here, if you want, you can say 2 pi over a. Okay, but if you don't want to say to some number, right here you can skip that, because we just need to know whether this improper integral is convergent or divergent. Okay, we don't really care about to what value. Okay, so the improper integral converges. That's what you get from the improper integral. Now remember the integral test. The integral test says that the improper integral and the infinite series will both converge or both diverge. Now you say that the improper integral is convergent, that means your infinite series will also be convergent. Okay, so let's finish this. Therefore, the infinite series summation k over k to the fourth plus 1, k start from 1 to infinity, this infinite series, okay, also converges. Okay, and don't forget, last time we talked about this, right? We will learn a lot of tests. Okay, so every time you apply a test, you need to state the name of the test. Okay, so this series converges because of the integral test. Okay, so by the integral test. Okay, by the integral test. Now here I have to warn you that a lot of students like to say, okay, this series also converges to pi over a. No. Okay, so again, in general, we should not infer from the integral test that the sum of the series is equal to the value of the integral. Okay, because in general, they will not be the same. Their values will not be the same. Okay, so the best thing we can say is that this series converges, and that's it. We don't know anything about the value. Okay, we just know it converges. Okay, so again, you can see that this is a very long problem, right? It takes us two pages. Okay, so usually, if you can use other tests, then use other tests. Okay, unless the problem specifically tells you, hey, you need to use the integral test, and then you will choose the integral test. Okay, again, this is a very long process because here you need to check the conditions. Okay, you need to check the conditions, and then you have to evaluate the improper integral. Okay, so that will be a little bit long. Okay. Now, finally, we would like to talk about. Okay, we would like to talk about the remainder of the integral test. Okay, so let's take a look at page 3, estimating series with positive terms. Okay, so right here, that f be continuous, positive, and decreasing. Okay, the reason we want to do this is because we want to apply the integral test. Okay, and of course, right here, let a sub k be f of k. Okay, now that s equals summation of ak, k start from 1 to infinity. So that s denotes the sum, okay, of the series. And right here, we assume it is a convergent series. Okay, we assume it is convergent. Okay, now notice that if it is a divergent series, then there's nothing to estimate, right? It's divergent. What do you want me to do? It's divergent, right? So if it is convergent, then we will talk about how to estimate the value, right? Okay, now with that s sub n be the sum of ak's, k start from 1 to n. So notice that this is the nth partial sum, okay, the sum of the first n terms. Okay, and the remainder, okay, the remainder we define it to be r sub n. We use the notation r sub n. R stands for remainder. Okay, the remainder is s minus s sub n. Okay, so r sub n is s minus s sub n. So notice that s is the true value of the convergence series. Okay, it's the sum of a k star from 1 to infinity. But S sub n is just the sum of the first n terms, so that means S sub n is the approximation. Okay, S sub n is the approximation. So if you have true value minus the approximation, then your remainder R sub n is your error term. Okay, is your error term. So basically, we want to see how big the error is. Okay, of course, when you estimate something, you don't want this error to be super huge, right? Right. For example, you say pi approximately equal 3.14, right? So you can say that pi minus 3.14 is your error term. Okay, of course, right here, if you say pi minus, so let's say I approximate pi using 5, right? This error is too big, right? This is not a very good approximation. Okay, so you want this error to be as small as possible. Okay. Okay, so now your remainder R sub n will satisfy this inequality. Okay, so R sub n will be less than the integral of f from n to infinity, and it will be greater than the integral of f from n plus 1 to infinity. Okay, so R sub n, your remainder, will be between these two integrals. Okay, so notice that right here, R sub n is s minus s sub n. So if you add s sub n to everything, you will get this result. So s will be less than or equal to s sub n plus the integral of f from n to infinity. And it will be greater than or equal to s sub n plus the integral of f from n plus 1 to infinity. Okay, again, the last inequality comes from the previous one. You just add Sn right here, add Sn right here, add Sn right here, and you get the following. Okay? Good. Okay, so let's take a look at example 2. It can be shown by the integral test that the series summation of 1 over n squared converges. Okay, now using the remainder estimate for the integral test, which bound on the remainder is correct when the sum of the first 3 terms of the series is used to approximate the sum of the series. Okay, so right here, first we notice that this is a p series, right? This is a p series, p equals 2, right? P equals 2. So we know this p series is convergent, right? Now I don't know if you still remember it, but previously we in our lecture we say that there's a connection between the improper integral and the p series, right? And this is because of the integral test right here. So see here, the integral and the series both converge or both diverge. Okay, so go back to your previous lecture notes and see the comment, right? The p series converges if p is greater than 1. The improper integral, the 1 over x to the p power, is convergent when p is greater than 1. Okay, so take a look at this part. Okay, anyway, now let's take a look at this problem. So we want to use the remainder estimate for the integral test to find a bound. So notice that the problem says that when the sum of the first 3 terms of the series is used to approximate the sum of the series. Okay, so basically this means we use s sub n to approximate s. Well, in particular, right here, n is 3. So how about this? We use s3. Okay, we use s3 to approximate s. So that means our remainder should be R3, and that will be S minus S3. Does that make sense? Okay, so you might be wondering, how do I get a number 3? Well, first, you can see the choices, right? Everything covers R3. Okay, but let's say this is a free response question. How do I know I have to choose n to be 3? Because we use the sum of the first 3 terms. Okay, first 3 terms. So that's why right here we have to choose 3. Okay? Now notice that R3, we want to find a bounds on R3. So according to our discussion, R3 should be less than the integral of f. Okay, so notice that your f, your function, should correspond to your series, right? So right here, your f should be 1 over x squared. Okay, your f should be 1 over x squared. So the integral of f from n to infinity, so from 3 to infinity. And right here, it will be greater than the integral of f from 3 plus 1, so 4 to infinity. Okay, 4 to infinity. Does that make sense? Good? Okay, so we want to evaluate these integrals. So let's evaluate the upper bound first. Again, this is an improper integral, right? Because you see infinity in the bound. So you have to write the limit first. Okay, the first step is always to write the limit. You want to integrate 1 over x squared from 3 to t as t goes to infinity. Okay, and this will be, what is the integral of 1 over x squared? Now if you forget, okay, here's the quick hint. If you forget, this is x to the negative 2. Right? So that's the power of x. You can use the power rule, right? Add 1 to the power and then divide by the power. Okay, add 1 to the power, divide by the power. So you have negative 1 over x. Okay, negative 1 over x from 3 to t. Okay, so as I say, I don't like these constant multiples. It always messes me up with the signs and my calculation. So let me take it out. So I have 1 over x, plug in the upper bound, plug in the lower bound. Okay, now when t goes to infinity, 1 over t will go to 0, right? Because you divide 1 by a large number, this will go to 0. Okay, so you have 0 minus 1/3, so that's a negative 1/3. Negative 1/3 times negative 1, so you have a positive 1/3. Okay, you have a positive 1/3. So that means your r sub 3 should be less than 1/3. It's okay? Now, of course, right here, this is a multiple choice question, so sometimes we can use some shortcut, right? Because R3 is less than 1/3, you notice that this is the only choice. Okay, so choose A. Okay, choose A. Now, of course, we have to pretend this is a free response question and do the practice, right? So right here, you will need to evaluate. Okay, you will need to evaluate the integral from 4 to infinity. Okay, so I will leave that to you. Okay, leave it to the reader. Okay, leave it to the reader. Okay, and basically it's really easy because you just need to copy copy everything right here, and then change this 3 to 4, 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 change this 3 to 4. So you get 1 over 4. Okay, you get 1 over 4. Okay, so I will let you write down the. Of course, Okay, so I have to warn you that you cannot do this on the test. Okay, if this is a free response question, you have to write down the full work. Okay, on the test if this is a free response question. Okay, I'm being sloppy right here because I want you to practice that on your own. Okay. So in this lecture, we talk about the integral test, and we also talk about the remainder for the integral test. Okay, so Notice that for the integral test, you need to create a function f, and to apply the integral test, you need to make sure it satisfies three conditions: continuity, positive, and decreasing. Okay, and then you need to evaluate the improper integral, because the improper integral and the infinite series will both converge or both diverge. Okay, so make sure you practice the problems on Canvas, and also it is highly recommended that you practice the problems on the all tests. Okay, we put them on the test because of some reason, right? So if you don't practice those problems, I think that's not good. Okay, so make sure you practice all those all exam problems. If you have any questions, please do not hesitate to let me know. Thank you.